And now it's a pleasure to introduce David Ruskic from the University of Genève, Switzerland. And he will give a presentation on modifier-assisted differential mobility spectrometry for quality and quantitative LC-IMS-MS analysis. And he will show the potential of DMS in multidimensional separation. So please, it's yours.
Good afternoon, everyone. And I would like to thank Chair for invitation for this talk. And I would like to start this presentation with this figure. And believe me, I won't going to talk about astronomy, but I took this figure just to show that is actually really nice, tight connection between instrument development and discoveries. So in 17th century, we could see only few satellites and planets based on primitive telescopes. But as technology evolved, thanks to astrophotonic era, we can see the first galaxies and discover the structure of the universe. Well, to see more brings more complexity, of course, that we have to deal with and then sort it out. But going back to the Earth, as a chemist, we would like to understand the nature at the molecular level. So for this, we need the tools to see the molecules, like spectroscopic or spectrometric devices. And in analytical chemistry, with respect to mass spectrometry, one of the biggest game changer was development of atmospheric pressure ion sources that allowed liquid chromatography connection to the mass spectrometry. Then we could resolve the molecules, ionize, detect, and characterize in the different ranges from the small molecules, metabolites, pharmaceuticals, to the really large ones, like proteins. And since then period, this area of research evolved drastically, like biology, like food, medicine, drug discovery. And there is always tendency to add dimensions. For quite some time in past 30 years or 40, we already been in 3 dimensions. That means time separation dimension, mass separation dimension, and fragment separation. So each of them brings a different sort of information. And because scientists always like to see more, then the vendors were pushed, like, what else we can bring to be able to see more. So one of the solutions is a 4th dimension, is the mobility dimension. Because new generation of the mass spectrometry, they always comes with the higher sensitivity, resolution, dynamic range, and so on. But in terms of isobar separation, it cannot help a lot because of M or Z. So they come with mobility dimension. An obvious reason because of it separates ions in the gas phase and very well matched to the mass spectrometry. And because of the speed of analysis, it suits exactly on this position between chromatography and mass spectrometry. And because also gives some different sort of information like collisional cross-section. And nowadays, commercially available IMS systems like what we've seen in previous session, drift time IMS, TWIMS, FAMES, DMS, and trapped ion mobility. Each of them works on different principal operation. But for those that are not familiar, I'll provide again some basic principle how they work. But what we can distinguish then between these collisional cross-section based devices and DMS and FAMES is the electric field they use, either low field or high field. This is one example of ion mobility at low field. So this is drift time IMS, which is one of the oldest one. Originally it was called like plasma chromatography, was connected actually to GC. But then after development of atmospheric pressure ion sources, it finds its place connected to mass spectrometry. It has a flight tube, which is made of these stacked ring electrodes, and uniform weak electric field is applied in that direction, while in opposite direction is applied the drift gas. So the ion coming into the drift region, they experience different average velocities, and it's proportional to the electric field. And proportionality constant K, it's well described with Mason-Champ equation, which shows correlation between reduced mass, charge, and collisional cross-section, which is something that tells about shape of the eye. If we increase the field strength, then something else going on. The mobility is getting as a function of the electric field, so it's not anymore constant value, and therefore we cannot use any more Mason-Champ equation. So this is why we cannot get the collisional cross-section information based on these devices. These two brothers, having the same origin, works basically in the same principle, just different geometries. We've seen in previous session about FAMES that was implemented by Thermo, has circular geometry, and SciEx is using differential ion mobility with planar electrodes. So the principle is following. So these two parallel plates, typically 1 millimeter gap and 1 centimeter long. It's in between the ion source and detector. So the ions are pushed by carrier gas, and this is the axial velocity, while radial velocity is given by so-called separation voltage or dispersion voltage in FAMES. So it has high and low amplitude, and this is type of trajectory that ion experience upon these two forces. So, because as I said that high field mobility is electric field dependent, we cannot get information about collisional cross-section, but to describe this is taken one polynomial function which can be written in simplified form like this, which represent normalized difference between mobilities between high and the low field. And when it's equal to 0, then ion has condition to pass through. If it's different than 0, then it will collide with electrodes. In order to correct trajectory, weak DC potential is applied, so-called compensation voltage, and it's ramped in order to get a full spectrum. Well, there are, in general, two mechanisms that describe ion motion in the DMS. One is hard sphere interaction, which can be described like this. So this is how COV behaves with increasing the separation voltage. What you see here is that mobility at low field is smaller than at the high field, because upon the acceleration of the ion, it will collide with the buffer gas and deflect. So the average path here is much longer than here. Well, DMS allows modifier use, so this typically polar organic solvent at small percentage. And what happens it's opposite. So now the ions drift negative, because the low field now allows ion clustering. And because of the cluster, ion gets bigger and consequently slower. So that's the basic concept. Just before I start with how we can improve the resolution in DMS, this is the orifice or ion sampling paint in front end of the mass spec. So in front there is these two parallel plates are embedded in the ceramic block, and on top of that there is specially designed curtain plate which has ion exchanges and ceramic beads to make sure that the organic solvent is in the vapor state. So one of the ways to improve the separation performance is to increase resolution of DMS. So that means improving or increasing the residence time inside the cell by increasing with the throttling gas to increase the pressure in that region here, and then we kind of are pushing the ions back so that they experience more cycles of high and low field at the cost of the transmission time, which goes from 7 milliseconds to 30. The other is to change selectivity by adding the organic solvent inside, like changing packing material for chromatography. And this is actually the effect. So if you take these three isomeric molecules, obviously with the exact same mass, and collisional cross-section. By using different modifiers, we achieve different separations. Not only resolution, but also changing the peak orders, which means changing the selectivity. Well, because as a chemist, I would like to know what's going on, because it seems that DMS fundamentally it's different than the other collisional cross-section instruments, because it's really dependent on the ion molecular interaction. So we decided to do some computational modeling to calculate what's theoretical binding energy, how that correlates or it's related to the separation. So here are two isomeric molecules again, and here as a modifier is used acetone, and here methanol. What you can see on these dispersion plots, red, blue, blue, red, means inverting selectivity. And this is calculating using DFT approach, the cluster binding energy, which you can see it's correlated quite nicely with experimental data. And the most prominent interaction of ion and the polar organic solvent is, of course, hydrogen bonding, then the quadruple ion interaction also that we were investigating. But I will not go too much in detail for this. I will just point out that because, as I said, fundamentally really different approaches, we can observe different results. Because as COV values are strongly related to binding energy, it's really orthogonal by using the modifier to the mass spectrometry, up to 500 daltons of the small molecules. So the same set of the molecules is used on the left and right. Here you see poor orthogonality, but you have information, collisional cross-section. And that's the drawback of the DMS and FAMES. So now it's time for applications. In our lab, we had since 2010 triple quadruple system with the DMS, because DMS operates something like a quadruple mass analyzer, either in filter mode or scan, and then logically is a fixed mode goes to the triple quadruple, and scanning mode to the QTOF for profiling type of analysis when we want to see more. Okay, I'll show first the applications that we done using the DMS triple quad. So in sort of application when time matters, DMS can help because of this additional degree of the separation. So here on top you see standard procedure for blood storage. And this is what happens over time with the red blood cells due to the oxidative stress. It changes the shape and then it gets bad. Glutathione is taken as a biomarker to assay the quality of the blood in its reduced and oxidized form. And Ms. Vera, she was developing high-throughput method based on short LC-DMS-MS method, using 1 centimeter column ethanol as a modifier for a DMS, and she compared it with the reference 20 minutes method with flow injection analysis, short LC-MS and short LC-DMS-MS method. So this short method was less than 1 minute, and here's actually, you can see the performance. So here it's reference method. Here it's flow injection because obviously it doesn't have any pre-separation method, and then high variability are expected. And then with DMS filter off or on, you achieve better performance for quantification. The other type of the application we've done with the OPP, that's open port probe interface. This is actually the photograph OL system, which Mr. Sosnovsky was working on that. So this is small PAL system that was adapted for sample handling. And open port is 3D printed, uses CLA 3D printer based on resin. And the other tools are printed with filament. So but just basic principle of OPP, it's based on Venturi effect. So relatively high gas flow for nebulizing gas is used in order to achieve this small vortex in the middle of the capillary. So the solvent methanol is pushed in the outer channel upwards, forming this little dome, and then in the middle, actually, where the analyte goes through being ionized and detected. So he was working on different designs in order to optimize the setup for maximum sensitivity and reproducibility. And what you can see here is the comparison between flow injection analysis and OPP. If you take a drug diluted in the water, 500 higher signal, it's observed in flow injection analysis than OPP. But once it's spiked in the urine with heavy matrix, then exactly the same response. It's because of the peak shape that is affected by, because flow injection analysis, almost 1 minute in the baseline, but OPP really helps to reduce the matrix effect. So this is what I like the most about this approach, is that contact analysis. So for sort of analysis where you don't need LC, and this comes really fast. So this is a standard method that is used for pesticide analysis in fruit, and because pesticides are on the top of the fruit, so why we do need the whole homogenized to analyze it. And here is just enough to touch the dome of the OPP, and then you have signal, and just for quick screening. And also the with respect to quantification, also performance, it's quite good regarding the accuracy and precision for drug molecules. This is because it's similar, like flow injection analysis doesn't have any pre-cleanup step, but DMS comes nicely here because it's separating the ions after deionization to achieve selectivity. And speaking of scanning, and the other instrument that I've showed on the QTOF that we have since 2018. So the experiment, to make experiment is fairly simple. Here is typical chromatogram, which is obtained. So each point in the chromatograph is full scan in the DMS, and each step in the DMS is full scan in MS. So again, we have now 3 dimensions. So the point in untargeted profiling is to get a bigger as possible peak capacity and separation in order to see everything. So preventing the performance of the chromatography and then expanding in the second dimension with a high orthogonality degree to separate as much as possible features or analytes. But we were facing at the beginning some sort of an issue that we wanted to sort it out afterwards. For example, this is set of 125 analytes. Using all the nitrogen, it's not a lot going on here, so we don't have this nice orthogonal separation. But once we switch to 1.5% of IPA, we got really nice orthogonality here. Well, improving orthogonality, but at the cost of the sensitivity and information loss. So why would we need that dimension if we lose information? So the reason is because IPA, it's highly basic solvent in the gas, and then due to the charge stripping, it wipe out your signal. Second of all, some analytes are shifting a lot, so exceeding the range of the DMS scan. This is another reason why we lose information. This is because Sykes decided to use peristaltic pump for Select-SIME. And it's limited rather to 1.5 or 3% mole ratio to the nitrogen, which was a bit annoying, but then we decided to do some modifications. So then solvent purity. Because constantly flowing the solvent here, no matter what purity is, will pre-concentrate the contamination, which will end up in your spectrum, leave the baseline, and then kill your signal. That's the other issue. Boiling point, viscosity, because peristaltic pump cannot accurately enough deliver the low viscosity solvents. And then I asked multiple times, Gerard, can I do modifications? And then finally he agreed, and I decided to put binary pump to do modifications. And then we start to work with binary solvent mixtures. So first step was to define the solvent that doesn't have any impact on the ion mobility. And because we've done previously some theory, it's normally expect the cyclohexane won't do anything, right? Doesn't have any polar functional group that can make a cluster. And indeed, it doesn't do anything. But once we start to infuse the IPA and making a mixture of these two, we have already at 5% spiked in the cyclohexane already dramatic shift, which is at minus 45 volts. And if you compare this to previously, okay, this is 100% IPA, so 1.5% mole ratio to the nitrogen, and this corresponds to 0.01% to the nitrogen gas. Most importantly, we prevent the information, so we have all signals there. Plus, because, well, less orthogonality does not necessarily mean less separation. Selectivity is what matters. So it was interesting to investigate further the effect, and I will say this looks a bit more complicated. I'll explain step by step. So this is again 3 isomeric molecules. The infusion experiment has been done. So everything was kept constant except changing the IPA concentration in DMS. So to see how modifier affect in the real time. And the cycle time was 0.5 seconds. So that means this heat map is practically area of the peaks of after each cycle. And then this is red, it's maximum, and black is medium values. So what you can see, this is we infuse the IPA in a gradient mode with the binary pump at 0% of IPA, so that means 100% of cyclohexane. We have this small plateau just to ensure that there are stable conditions and nothing affecting the COVs. And as soon as IPA reaches the DMS, there is a dramatic shift here, really steep line, and then goes down, and you see this crossing, and then until we reach saturation point where COVs are not changing anymore. And then at that point it was clear for me why SciEx didn't allow me to work below 1.5%, because this is what gives the most accuracy with peristaltic pump. Here, if you change a bit of composition, you will have high variability. So you really need to make sure that you have stable flow of modifier. But how much it's lost, it's obvious here. So 35 less signal, it's over here, and then here you have more separation. Well, it's not always, it's analyte dependent. So at least this approach will give you a possibility to tune the separation. It spreads out the possibility of the DMS. So then we start to implement this method for profiling type of analysis, and what you can see here, this is a pure nitrogen. This is 0.1% of IPA with LC. You see, we don't need to scan really large DMS windows, so we compress it a bit to get cycle time below 1 second, typically 0.8, which gives you also quantification, better quantification performance, and really nice orthogonality to LC. And as a last, so binary modifier mixture gives you many benefits with respect to the background ions, with the sensitivity loss, separation tuning, and so on. For future perspectives, so bringing now 4th dimension, which is MS-MS. This is now what we are currently working now based on SWOF data analysis. And this is just one example how it can be beneficial. So DMS can separate, you see this small peak here, like a multipairs from electrospray, that you can have a pure MS-MS data. And this brings me to the conclusion. So modifier-assisted DMS shows a high orthogonality degree to both LC and MS, and unique, because of unique separation mechanism. The fast tuning of analyte separation using modifier helps fast method development. COV can be also used as a library for analyte identification, why not, like CSS, and also for future perspective, bring MS-MS as well for 4-dimensional separations. Thank you very much.
Thank you very much for this nice talk about fame.